make sure my mic is working. Yep. A class that I taught yesterday. I taught the whole class and I stopped the video and then it error messaged out on me and I lost it. So just note that might happen. Hopefully it won't, but it happened yesterday to me. But I wasn't in this classroom, I was in a different one, so maybe it won't happen in this classroom. Okay, so we just learned about linear combinations, spanning, how to write solutions to systems as the span of a set, and how to write them in parametric vector form, right? Now we're going to talk about what is linear independence, and it's related to all that stuff that we just went over. So linear independence says if you have a set of vectors, they are linearly independent if the homogeneous equation, what is a homogeneous equation? Well, here it's written as a vector equation where I have these vectors in a linear combination where the coefficients x1, x2, all the way up to x sub p are the weights, and we wrote it in our last class as a matrix equation, and it's homogeneous if the right side is the zero vector. Okay? It's non-homogeneous if that right side is not zero, not the zero vector. So these vectors are linearly independent if the homogeneous equation has only the trivial solution. We talked about what does that mean? That means you have three variables when you solve the system. Okay. So if you solve a system and there are no free variables, then the vectors in your matrix, the columns of your matrix, are linearly independent. Okay. What that means in this equation, instead of looking at the homogeneous matrix equation, you just say x equals 0 is the trivial solution, right? You plug in 0, you get 0. And this equation means that every weight or every coefficient of these vectors, or every scalar multiple of those vectors, is 0. That's the only way you're going to get 0 in the end. The only way to make a linear combination of these vectors equal 0 is to multiply all the vectors by 0. And that's what linear independence is. If a set of vectors is linearly independent, then it is not possible to write one of the vectors as a linear combination of the others. So if the only way to make this equation work is to make all the scalar x's 0, then what does that mean for this equation? If I move this to the right side, this work is to make all of these x's 0, which means I can't write vector v3 as a linear combination of v1 and v2. See that? I can't come up with three scalars that'll make this equation true where this is just v3. The only way to make this true is to make all these coefficients 0. Okay? And you can move any of these over and see that, right? So that's one of our main results of linear independence. While we're interested in linear independence, that any of the vectors you cannot write as a linear combination of the others. You can't construct or you can't construct any of the vectors in the set with the other ones in the linear combination. Okay? And then linear dependence means that they're not independent. Okay? So it means that you do have non-trivial solutions to the homogeneous equation. So it means you do have free variables. If you solve a system and you have free variables, that means you have non-zero solutions. And if a set is linearly independent, then it is possible to write at least one of the vectors as a linear combination of the others. It may not be, you may not be able to do all of them that way, but there's at least one vector in there that you can rewrite your combination of the other vectors. So, are the following vectors dependent or independent? So how are we going to figure this out? So the definition of linearly independent says the homogeneous equation has only trivial solutions. So x1u plus x2v plus x3w equals 0. If the only way to make that work is for all the x's to be 0, then they're independent. So you can read this as a matrix equation where A is these vector columns and x is x1, x2, and x3. Okay, the weights that I'm going to multiply. Right. Remember, that's how you multiply a matrix times a vector, right? You take each entry of the vector and you multiply it times the columns of the matrix. Okay, so we're just going backwards there. So we're going to put these columns in a matrix. And I'm augmenting with 0, right? Because it's a homogeneous equation, I'm going to go ahead and augment with 0. Do you have to augment with 0? You don't really have to, because nothing's going to change. You know, column. All your row operations are not, nothing's going to change with these zeros. There'll be 0 at the end as well. But you know, we want to, or I would rather know what I'm doing instead of always finding the shortcut way, and then I have to memorize that shortcut way. Does that make sense? So let's just understand what we're doing and just do it. But I'm not going to count off if you don't augment. I will count off if you augment when you're not supposed to. That, you know, don't augment something that's not augmented. Okay. But if you don't augment this with 0 and you mess this up, then I'm going to suggest that you augment with 0 so you understand what you're doing. Right? We're solving a system that's set to 0. So I'm going to cheat and use the calculator. Does that bother you guys that I say that? I've had students complain. It's not cheating if you use the calculator. You can use a calculator on every test, except the first quiz. Yep.
Does any of the calculators support using variables?
It will not.
That's sad.
So that means that if I give you a problem on the test that has A inside the matrix or inside the vector, you're going to have to do stuff by hand. Okay. So if you can't row reduce by hand, and if you can't do it with a variable in there, you need to fix that now. Okay. Don't wait till the night before the test to try to figure that out, because it's not going to be good. Okay. So row reduce. I like fractions. Okay, let's do this. Let me split screen this. All right. So do I have free variables? I have one. That means that these are dependent. I have a free variable, so they're dependent. So what that means is I can write at least one of these vectors as a linear combination of the other two. And I actually know exactly how to do that based on this, what we just did. If I were to, let's just do this in green. Let's say forget the 0. Let's augment here. And I'm saying, give me two weights. We'll call them C's, but they could be X's. Okay, just to make it different. I need weights to multiply by this vector and this vector that'll equal that vector. And I solve this, then it's augmented here. What are the weights? 2 and negative 1/3, right? So if I multiply u by 2 and I multiply v by negative 1/3 and add those together, I'll get w. See that? Let's see if that works. Let's multiply u by 2. Use a different color so we're not confusing ourselves here. Multiply v by negative 1/3. So 6 divided by 3 is 2, so it's negative 2, negative 1, and positive 3. Is that right? What do you get when you add those together? You get w, right? So that means that they're not independent because I can write one of the vectors as a linear combination of the other two. It's 2 times u minus 1/3 v is equal to w, so they're not independent from each other. Yes?
Is that because of the, so you have 2 and minus 1/3 through the thing?
Yep.
So those correlate to the coefficients?
Well, I said if we make a new system where I'm augmenting here instead of with 0, then I've got C1 times U plus C2 times V equals W. Solve for C1 and C2. Right? And the row reduction is the same. Right? So we've solved for C1 and C2. C1 is 2, C2 is negative 1/3. Right?
Will we need to do that, or can we just stop when we get the free variable?
I'm just showing you that to explain what we mean by you can write one as a linear combination of the other two. And you can tell, when you get the free variables, you can tell why that is. 2 and negative 1/3. 2 times u, negative 1/3 times v. Add them together, you get w. Right? This is 2u minus 1/3 v equals w. Right? That means I can write one of these vectors as a linear combination of the other two, so we say they're dependent. If we threw out w, we threw it out, and I just put u and v in my set. So I just have these two vectors, and I augment with 0, and I throw out w. Do I have free variables when I row reduce? No, right? That means u and v are independent from each other. But you add the w in, they're not independent. Another way to say this is if I spanned U and V, I'd get that plane, right? Span two vectors in R3. In fact, they have to be independent. So we didn't tell you that before, but if they're independent, you get a plane, and W happens to be in that plane. W is in that plane that you get when you span these, because when you span, you get every linear combination possible, and that's one of those possible, and that's W, 2U minus 1/3 V, right? So if the vectors are linearly independent, determine a non-trivial relation. So what's a non-trivial solution that'll give us 0? So let's solve the original system, right? So we have x1 plus 2x3 equals 0. x2 minus 1/3 x3 equals 0. And then x3 is itself. And we'll solve these for each one, right? So those are the solutions to that system, right? That homogeneous equation. Those are the solutions. We need to come up with an example. So x1 is going to get multiplied by u, and x2 is going to multiply by v, and x3 is going to multiply by w. So let's let x3 be something nice. We can't make it 0, right? That would be the trivial solution. All right, we're looking for non-trivial. You could choose 1. I'm going to pick 3 just to cancel this fraction out over here. It's going to make that one 1, and this will be -6.
So you can pick any number first.
Any number, it's going to work. Yep, any number for x3, and then you calculate x1 and x2, and it'll work. 0 will work, but it asks for non-trivial. 0 will give you trivial. Yeah. We're not interested in the trivial one because it's obvious that 0 works, right? We want something that's non-trivial. So if you want to know if they're independent, you can put those vectors in a matrix, row reduce it, augment it with 0. If you have free variables, they're dependent. If you don't have any free variables, they're independent. If they have free variables, that means that you can write one as a linear combination of the others, at least one. There may be others. If they're dependent, you can get non-trivial solutions for the homogeneous equation. Okay? You can get non-zero solutions when you set it equal to 0. Are we good? Questions? So on this one, all we had to do was the blue part where we found out we had a free variable and we just say dependent. The rest was just trying to help you understand what's going on. Okay. All right. Are these dependent or independent? So if we put these in a matrix, augment with 0, and row reduce it. I'm going to do this real fast without a calculator. You guys ready? I'm going to do this real fast. Okay. I'm going to put this last row in the top. I'm going to put the top row at the bottom. So I just swap the first and third rows. See that? Okay. So I just swapped first and third rows. Everybody okay with that? Okay. So I had these zeros here, right? And a 0 here. Can I make that -3 a 1? So divide by -3, right? It's not going to change the zeros. Everybody agree? Okay. I can use that 1 to eliminate these two. Do you agree with that? And when I add a multiple of this row to these two rows, are these zeros going to change anything else? Right, so let's say this is a 1 now, and I'm going to multiply it by -4 and add it to this one. If I multiply these zeros by -4 and add them, it doesn't change these other ones. Does everybody agree? So I make that a 1, I can make those 0. Okay. Let's just do that. Right? That happened. We all know how we could do it that way, right? But I just wrote it down. Okay. I've got this 5. Can I make that a 1?
Yes.
I've got zeros everywhere else. Is that going to change anything else? No. Can I make this? And I'll use that 1 to make that a 0, right? And then can I make that 2 a 1? Okay. So we're done. Yeah.
Is that second one actually similar?
What do you mean similar?
Like when you change that to a 0, wouldn't the -8 change? Or no?
Which one? When I made which one 0?
On the top row.
So from here to here?
Yeah.
So I made that 1.
Correct.
I used that 1 to make these 0.
Since the other ones in that row were 0, it doesn't matter.
These are 0, so they don't change anything else. Right? Because I'm adding 0. Right? And then I made this a 1 and made that -8 0.
So how many row operations was that?
I don't know. Say 1, 2, 3, 4, 5, 6 of them. And really I knew that I could have went right to there. Because if you have a 3 by 3 coefficient matrix, or if it's square, and you got it into triangular form, it will reduce to that every time. Okay? For the reasons I just talked about. If it's triangular and those are 0, then I can make that a 1. This has to be non-zero, okay? It has to be the triangular form where this is non-zero and these are 0. Actually, I knew before at the very beginning, because that triangle, same way. Okay? I could have row reduced backwards. I could have made those 0, made that 0. But anyway, so when we row reduce this, do we have free variables? No, so they're independent. And you know they're independent if you get that triangular form, automatic independent, okay? That means automatic you get unique solutions too. You're not going to have free variables, you're not going to have multiple solutions, or infinitely many. You're going to get one solution. Yep.
Isn't your one solution 0 though? No.
Yeah. Yep. So that's what independence means, is the trivial one is the only one you can get. It's the only solution you have to that homogeneous equation. Questions? You guys are whizzes at row reduction by now, right?
The calculator is.
The calculator is, but the calculator, sometimes it can mess up. So sometimes there's a row operation that requires some rounding to go on, and then that rounding can get compounded when you do all these other operations to it. You can end up, if you're doing a bunch of them, big matrix, it can mess up.
I'm sure my lunch class is okay with low tolerance.
Well, okay, we already talked about all that stuff. So here's some tips to help you check dependence. If a set contains more vectors than there are entries in each vector, then the set is linearly dependent automatically. That means your coefficient matrix has more columns than it does rows. They're automatically dependent. If you have more rows than columns, that's not the case. You can still get independence with more rows than columns. So, remember when I said if I just take these first two, they would be independent, right? There's 3 rows and only 2 columns if I just take the first 2. Okay? But let's say we were doing this last one. If I added another vector on the end, and I had 4 columns and only 3 rows, the first 3 rows would still reduce to this, and that 4th column would have to be a free variable. Okay? So if you've got more columns and rows in your coefficient matrix, I'm not talking about when you augment. In your coefficient matrix, if there's more columns than there are rows, then it's automatically dependent. You're going to get free variables. Guaranteed. Another way to say that is you have more vectors than you have entries in the vectors. So if you have R3 vectors and you got 4 of them, that's too many. Your set's going to be dependent automatically. If you have R10 vectors, but you've got 15 of them, they're independent. Okay? I mean, dependent. They're dependent. Automatically dependent. Any system containing the 0 vector is dependent automatically. If you've got a 0 vector, your set is dependent. If you have a 0 vector, it never changes in row operations. That means you can't get a pivot entry in that column, which means that column is automatically a free variable when you solve the system. Okay. 2 vectors are linearly dependent if one is a scalar multiple of the other. So I said the set is dependent if one of them can be written as a linear combination of the others, right? Well, what if you just see that 2 of them are just scalar multiples? One is scaled twice as big as the other one, right? Then that's automatically that one vector, one of those vectors is a linear combination of the others, because you can say this vector is 2 times this vector plus 0 times the rest, and you've got a linear combination that'll form that vector. So if any 2 vectors in your set, if they're scalar multiples of each other, then they're dependent automatically. So some of these you can just tell by looking at them. You don't have to necessarily row reduce every time. So let's see if the following are dependent or independent. What about the first one? We're not going to row reduce it. Is it independent or dependent? Dependent. Why? This one is 2 times that one. So it's really the same. It's a vector, 2 vectors on the same line, right? So they're not independent. So these are dependent. What about the next set? There's only 2 of them, right? Are they scalar multiples of each other? They're not. that means we cannot write one as a linear combination of the other one. There's only two of them, right? I can't write one as a linear combination of the other one because just a linear combination of the other one would have to be a scalar multiple of that one vector, and it's not. So these are automatically independent. Without having to row reduce them. But if you row reduced them, you would get a system with no free variables. What about the columns of this matrix? Are they dependent or independent? Dependent. Because I have a column of zeros, so if one of my vectors is a zero vector, it's dependent automatically. When I row reduce, these zeros cannot change. They will stay the same. I can't get a pivot entry in there, so it has to be free. So this one I already know how it row reduces. Right? I can make this 2 a 1 and these 0. That's going to stay 0. I can make that guy a 1 and make the other 0. So that's how it row reduces. Okay, what about the columns of this matrix? Right, so I have, if the columns are vectors, there are 2 vectors. They're size 2. I have 3 of them. So I have more columns than I have rows dependent. I don't know how that row reduces, but I know I have at least one free variable. I have to have one. What about this guy? How do I know it's dependent? This is a hard one, but I can tell by looking. So how do I tell? If you can't figure it out, then you put it in your calculator and row reduce it, or you row reduce it by hand, and you see, okay? But I can tell by looking. So add the first 2 columns. What do you get? If I add the first 2 columns, what do I get? So let's call this V1, V2, V3, V4, okay? V1 plus V2, what is that? It's V4, which means I can write V4 as a linear combination of the others. So how do I do that? I say 1 times V1 plus 1 times V2 plus 0 times V3 equals V4. That means they're dependent. So we'll get a free variable if we row reduce it. And sometimes that's hard to see, and it's okay. Your last resort is to row reduce it and see if you have free variables. Okay, that's your last resort. Don't make it the first thing you do every time. Sure, come to me and say, that test took way too long, Mr. Wellman. I'm going to say, no, it didn't. You know, you missed some easy things. You know, you went the hard way, so you don't have to do the hard way every time. All right. Yes.
So if there was a variable in the third column, then you won't have to worry about it, right?
Yeah, it wouldn't matter. It's dependent no matter what that variable is. Yep. Yes.
So there's more columns than rows. It's dependent.
Yes.
Then how come for example 2, I mean there's more columns than rows, but then for example 1, there's the same amount and it was no. I'm talking like previously. Yeah. For that one, like isn't there 4 columns?
No. In the coefficient matrix. Just in the coefficient matrix, not with the augmented form.
Thank you.
Not, don't count that one. Just in the coefficient matrix, if there are more columns and rows, then dependent. And the reverse is not true. You can't say because there's more rows and columns. That doesn't work. Okay. All right, so now for what values of h is the set of vectors linearly dependent? So this says because linear dependence indicates it's possible to write one of the vectors as a linear combination of the others. An alternate way of asking the question would be for values of h, is w in the plane spanned by u and v? Right, so if I span u and v, get a plane, and is w in that plane? And for what value of h would w be in the plane? Now we can look at it and try to see, is there a way that we can come up with a linear combination of u and v to equal w and see how it would work to get h. Does anybody see a way before we row reduce? No, we may have to row reduce. I don't see it yet, so I'll give you a chance. Yeah.
Take the absolute value as an operation.
No. No. That'll mess a lot of stuff up. Don't do that. Yeah.
Could you multiply vector u 6 and then add them?
6. Okay. Let's try that. So 6 u plus v. Okay. Let's try that. So 6u would be 6 minus 5, negative 6 plus 7, and negative 18 plus 8 plus h. Or no, equal h. 1, 1, negative 10. So that matches w here and here. So what does h have to be in order for it to work? Negative 10. So you figured it out. Good job. So h has to be negative 10.
Would there be another possible solution?
Probably not. If u and v, are u and v multiples of each other? So they're independent from each other. So that means this is the only solution. That's the only way to do it. 6u and 1v we'll make this h negative 10, and that's it. But if you wanted to figure it out the other way, then you would put these in a matrix augment. You could augment here if you wanted to, or you could augment the whole thing with 0, and then see what h will give you free variables. go to 1.8. Now this says required Khan Academy video. You don't have to watch a video, but maybe you should. But it's in the homework. But I'll try to explain as much of this as I can. So 1.8 is called matrix transformations. So way back when, probably pre-Cal 1 or maybe earlier, you learned about functions. Functions have domain and range. Functions also have domain and codomain. And we have this notation to write functions just to state what's the domain and what's the codomain. So the codomain is where the range is. Okay, but the codomain is might be something bigger. Okay, so we say function f is a mapping that associates a member from the set X to a member of the set Y. So you plug in something in the set X, and the function changes it and turns it into something that's in the set Y. Okay, so if you think about this kind of definition, right? You plug in a number from a set, and it spits out a number, right, from maybe another set, or maybe it's the same set. But what you say is the stuff you plug in domain, stuff that comes out is the range, and where the range sits is called the codomain. Okay. So when you write your function or your mapping out like this, you're stating the range and the codomain. I'm sorry, the domain and the codomain. The domain is the X, and the codomain is the Y. Now this is more important now rather than before. Before you were usually dealing with just the real numbers. So your domain was something in the real numbers, and your codomain was something in the real numbers. But now we have all these vectors of different sizes. We have all these different sets of things. R2 vectors, we have R3 vectors, we have R5 vectors. Okay. So we can have all these different possibilities of what gets plugged in and what gets outputted at the end. Okay. So we have this example. Let me write it bigger for those that don't have it. So we say H is a mapping that takes R2 vectors and turns them into R3 vectors. So you plug in an R2 vector and it outputs an R3 vector. So we say the domain is R2 and the codomain is R3. Now, all of R3 may not get mapped with this function, with this mapping. So what actually gets mapped is called the range. Okay? So your output vectors may be R3 vectors, but maybe they only output to a plane in R3. The plane would be the range, but the type of things that get outputted is R3. So R3 is your codomain. Okay. And we have this definition. It's kind of a horizontal way to write these inputs. So we're inputting two values. These are the two entries in an R2 vector, right? And we're going to output three things. We're going to output the sum. We're going to output the difference. I'll run out of room. We're going to output the product. So we get three things that get outputted. Those will be our three entries in our R3 vector. So an alternate way to write this would be like this. We plug in the R2 vector, and And what we get is an R3 vector. And this is how to construct it. That. So we are interested in functions that will map one space to vectors in another space just by multiplying by a matrix. And we call these particular functions matrix transformations. So we want a particular thing to happen when we write this function. Okay? And if we can make this thing happen by multiplying by a matrix, then that's called a matrix transformation. So this is just a transformation, transforms a R2 vector into an R3 vector. Okay? If we can accomplish this by multiplying by a matrix, we call it matrix transformation.
Can I give an error? Try to do that.
Say it again?
I remember when I tried to multiply two vectors and they were and it wouldn't do it.
Right. We have to find the right matrix that will work. If it doesn't work, then it's not right. We have to, or maybe we can't do it. You know, so not every transformation can be written as a matrix transformation. Okay. But we'll figure out which ones can. Give myself more room here. So a transformation, or you can call it a function, or you can call it a mapping. So they're kind of interchangeable. A transformation, we're going to call it T, from Rn to Rm, is a rule that assigns to each vector x in Rn a vector T Rm. So instead of f of x for function, we're going to call it T of x for transformation. And the x that gets inputted is going to be a vector, and the T of x that gets outputted is going to be a vector. They might be different sizes. They could be the same size. Okay. So x that we plug in is a vector in Rn in this example. The T of x that comes out is also a vector. It's in Rm. It's whatever size is in codomain. So a matrix transformation is a transformation T that is associated with some matrix A that acts by left multiplication. So your definition just becomes A times X. To plug the X into the transformation and perform the transformation, all you have to do is multiply on the left by the matrix A. Okay? And those are the ones that we're really interested in. And this says if T is a mapping from Rn to Rm, then A must be m by n. So we know what size it has to be in order for it to work. The domain of T is the space that's being mapped from. It's determined by the number of columns of A in the matrix transformation. So when you multiply A times X, right? And A is m by n, and we multiply by a vector x, right? That x has to have the same number of entries as A has columns, right? In order to do the multiplication, those have to be the same. Right? So that's what this is saying. It is determined by the number of columns of A, what the domain is. The domain is going to be what vectors are we going to plug in? What vectors can we plug in? Yes?
Is that n by 1?
Yes. And the codomain is a space that's being mapped to. It is determined by the number of rows of A, because what you get after you multiply these is some other vector And it has to be m by 1, right? It has to be the outside values. So the domain is what kind of vectors you're plugging in. The codomain is what kind of vectors get outputted. And what we'll call the range is the actual vectors that get outputted. Everything in the domain can be inputted. Okay, we want to make these where you can plug in any vector. Okay, so the domain will be the entire Rn space, right? But the codomain will be the entire possible number or possible vectors that could be outputted. The range are the ones that are actually outputted. And then we say the image of x is the vector t of x. So it's just a name we're going to call it. So when we have an x in the domain and we multiply that x by matrix A, we get a new vector. That vector is called the image of x. So in this picture, we have our our domain. It's Rn, it's whatever it is, set of vectors of the same size, and we pick a vector that we're going to plug into the transformation. So T is the name of the transformation. We're going to multiply by a particular matrix to get a new vector. That new vector is T of x. That new vector is called the image. That's true of functions too. You just probably were never told that. When you say f of 1 is 4, then 4 is the image of 1 in this function, or under this function. And then the range of T is the set of all images. It's everything that actually gets mapped into the new space, into the codomain Rm. For a matrix transformation, the range is a set of all linear combinations of the columns of A. So it's a span, right? So if you're multiplying by matrix A and you plug in every single x from the domain, what do you do when you multiply a matrix times a vector? You create a linear combination of those columns, right? You take the entries of x and you multiply them by each vector and you add them up. That's a linear combination. So you're finding every linear combination of these columns of A, it ends up being the span of the columns of A. So the range on one of these kind of transformations is always the span of the columns of A, and or you could just say it's all linear combinations of the columns of A. And these transformations are really awesome. We can make them do all kinds of things. Okay. All right. So let's just look at this example and see if we understand what I was talking about. So we have a transformation T. The domain is R2. The codomain is R3. That means we're going to plug in R2 vectors. We're going to output R3 vectors. So the transformation is defined by this rule. We take the two entries of our R2 vector, x1 and x2, and we get these three entries in R3 in an R3 vector. So the first one's x1 minus x2, the second one is 3x1, and the third one's negative x1 plus 2x2. And you can define this with a matrix transformation if you use this matrix A. I want you to look at the matrix A and look at the definition of the transformation, and you tell me if it makes sense. I were to multiply this by my vector x that I'm plugging in, that has entries x1 and x2, what do? We talked about two ways, right? We did the linear combination. You multiply the first column by x1, the second column by x2, and add them together. So is that what happens? x1, 3x1, negative x1, added to negative x2, 0x2, and 2x2. See that? Or we talked about doing those dot products. Remember the dot product? So if I take the first row of A, dot product with this vector, I get x1 minus x2. And in the second row, 3x1, 0x2. And the third row, negative x1, 2x2. Right. So that's it. So that was actually A part. So we multiplied by x1 and x2. We got, if we multiply these, we get this. Just like that. So what is the domain and codomain of T? T is the transformation. The domain is the set of vectors that we can plug in. So what kind of vectors can we plug in? What size are they? R2. Domain. Size of the vectors that come out. R3. And that is given in this mapping definition. It tells you, now sometimes maybe I won't tell you that on the test. You have to figure that out. But I think it's easy, right? We plug in an R2 vector, and what comes out is an R3 vector. Okay, given this U, find T of U, which is going to be called the image of U under the transformation T. So if I have this U and I want to find T of U, I want to transform this R2 vector into an R3 vector. What do? I multiply A times U. Right? It's a matrix transformation. We know what the matrix is, so matrix A, and I'm going to multiply by U. That's going to give me the image. So it's 1, 3, negative 1, negative 1, 0, 2. I'm going to multiply by negative 1, 5. You could also use the definition, right? But this matrix multiplication is going to do all that for us. So let's just check. 2 by 1 x, I'm going to get a 3 by 1 result. That's the R3 vector. Let's do the dot products because I like that better than the other way. So let's do dot product vector multiplication. So the first entry will be the first row of A dot product with this vector U. So it's going to be negative 1, negative 5, so it'll be negative 6 when you add them together. Negative 1, negative 5. Negative 1, negative 5. Like that. Okay, what about the second entry? Negative 3 plus 0. 0 times 5 is 0. So it'd be negative 3. This is positive 1 and 10, so it's 11. So there's the image. So this is T of U. That wasn't hard to do, right?
So all that stuff you were showing us before, like that was basically just to say that when you multiply those two, you're bringing it from like the picture with the plane. Is that bringing it from? Is R2 two dimensions and R3 3?
Mm-hmm.
So that's like all that before was just to show that basically, because this is the only math you have to do, right? With the
It's not the only math. But all that other stuff with math too. So this understanding functions and how they work and finding range and domain and all that. We have to know that language so that when you get this question, find the image, you know what to do. It's not hard to do. You just got to know that's what I've got to do. So you need to know what find the image means. What is the output of vector X? It's the image of that. It's the result. It's the output. Okay. Yep.
Isn't A a set of two R3 vectors?
No, it's not. It's a matrix of two. It's not. If the question asks for a set of vectors, don't write them in a matrix as your answer. Because a matrix of vectors is not the same as is set. These are my vectors in the set, separated with a comma, close it off. Set of vectors. And a matrix that has column vectors in it, you could write it this way, you can write it like that, but it's in a matrix, All that stuff we went over before is to teach you the language of what we're going to do next, okay? Because the questions are specific to the language, specific to the definitions, what we've gone over, okay? Find the codomain. What is that? It's not hard to find, but you got to know what that is, okay? So, I may not have time to do this. Let's just talk about how to do this. And then we'll do it next class. Okay? So determine if this vector is in the range of T. Where's the range? The range is in the codomain, and it's what actually gets mapped into the codomain. Not every R3 vector is in the range. The range is what is actually outputted from the function, or from the mapping, or from the transformation. So is this vector in the range? That means, can we find a linear combination of the columns of A to get this vector? So what this is saying is, if this is T of X, what is X, right? Or is there an X, really is the question. Is there an X? Right? So how does the transformation work? We multiply the matrix A times the X to get the output so how do you figure out if there's an X? If you knew this matrix and you know this vector here, how do you find X? You augment and you row reduce it, right? See if there's a solution. If it's in the range, because there's an X that I can multiply A by and it'll give me this vector. Okay? That's not new, right? This question is new. The work is not new. You already know how to do it. Okay, so you just have to know what is being talked about here. Okay? Yes.
So when we do that, there'd be a 0 in our thing?
You're going to augment the matrix A with this vector, not with the 0 vector, with this vector.
So, but like, what if we have, if there's multiple, or the last one we did, right, the example, it was 2 by 1, right? It was 3
Are these multiples of each other?
No.
That means they're independent.
Right.
That means if you set it to 0, the only thing you're going to get is a 0 vector as a solution, but we're not setting it to 0.
But we're doing 3 by 2 multiplied by 2 by 1, right? So on this one,
Let me see what it is. 1, 3, negative 1. Negative 1, 0. 2, augment with this. You want to see, is there an x1 and x2 that'll make it work? Those are the variables of the system. Is there a solution for x? I'm out of time.
So the actual